The average American engine almost never dies in one dramatic moment. Most people imagine catastrophic failures when they think about engines wearing out, pistons exploding, connecting rods snapping, clouds of smoke pouring from beneath the hood on the side of a highway. But the reality is far quieter than that. Engines usually die slowly, invisibly, over years of microscopic damage accumulating one cold start at a time. Every morning, before oil pressure fully builds inside the engine, bare metal surfaces briefly operate with minimal protection. Camshafts rotate against lifters. Bearings begin moving under heavy load. Timing components scrape across guides and tensioners. Thousands of precision machine surfaces wake up dry before lubrication fully circulates. Those first few seconds seem harmless because the engine still starts, still idles, still drives normally. But over the life of a vehicle, those tiny moments repeat tens of thousands of times. Each startup removes microscopic amounts of material from inside the engine until eventually the wear becomes impossible to reverse. And in quiet rural communities across Ohio, Pennsylvania, and parts of Indiana, older mechanics still talk about this problem differently than most modern service departments do. Years ago, during a freezing sleet storm in Holmes County, Ohio, an old machine shed stood vibrating under the sound of ice hitting the metal roof hard enough to resemble gravel. The building smelled of diesel fuel, gear oil, wood smoke, and cold iron. In one corner sat an aging Dodge pickup coated in farm dust and winter road salt. The odometer had rolled past 400,000 miles long ago. Most drivers would assume an engine with mileage like that should already be worn beyond saving. But when the truck started, the idle sounded almost unnaturally smooth. No loud ticking. No heavy vibration. No cloud of blue smoke from the exhaust. The engine settled into a calm, steady rhythm like a machine half its age. The owner, an elderly Amish mechanic named Eli, leaned against a workbench while warming his hands beside an old stove. Most engines don't fail because people use them too hard, he explained quietly. They fail because people start them cold thousands of times and never think about what happens inside during those first seconds. That sentence lingered long afterward. It led into old maintenance manuals from the 1940s, industrial engineering journals buried in archives, lubrication studies from heavy equipment manufacturers, and forgotten discussions among mechanics who spent entire lifetimes rebuilding engines by hand instead of replacing vehicles every few years. The deeper the research went, the stranger the pattern became. Modern drivers are taught to believe that synthetic oil solved nearly every lubrication problem. Commercials show golden oil instantly coating moving parts under perfect lighting conditions while engines gleam like surgical equipment. But actual engines rarely live under perfect conditions. After sitting overnight, gravity drains much of the oil into the oil pan. On cold mornings the remaining oil thickens. When the key turns, the oil pump begins working immediately, but circulation still takes time. During those moments, upper engine components experience what tribology engineers call boundary lubrication conditions. That term sounds complicated, but it describes something simple: metal parts moving before a complete protective oil layer forms between them. Those brief periods create a large percentage of long-term engine wear. Short trips make the problem worse. Many modern vehicles spend their entire lives traveling only a few miles at a time. The engine starts cold, warms partially, then shuts off again before reaching stable operating temperature. Moisture and fuel contamination remain trapped inside the oil. Condensation builds in the crankcase during winter months. Internal surfaces repeatedly cycle through cold starts without long enough operation to fully clean themselves internally. Older mechanics understood this decades ago because they rebuilt engines constantly and physically saw the wear patterns inside. Worn cam lobes. Scored cylinder walls. Timing chains stretched prematurely. Valve train sludge coating internal surfaces like tar. They noticed something else too. Engines used for long highway drives often survived dramatically longer than engines used only for short daily commutes, even when both received regular oil changes. That observation eventually led many mechanics toward one unusual compound: molybdenum disulfide. Most people today have never heard the name. Others recognize it only vaguely from specialty lubricants or industrial greases. But among certain mechanics, machinists, diesel operators, and heavy equipment technicians, moly developed a reputation that bordered almost on folklore. Physically, The substance looks unimpressive. A dull grey powder, soft and fine like graphite dust or fireplace ash. But at the microscopic level, molybdenum disulfide behaves differently than ordinary oil. Oil flows across surfaces and eventually drains away. Moly bonds directly to metal. Under pressure and heat, it forms an extremely thin low-friction protective layer that remains attached even when oil circulation temporarily disappears. In practical terms, that means engine components retain some protection during cold starts before oil pressure fully rises again. To older mechanics, the idea made perfect sense. One retired machinist described it in blunt terms while rebuilding a tractor engine inside a dimly lit barn workshop. "Oil is temporary," he said. "Moly stays behind." The history of the compound stretches back much further than most drivers realize. During World War II, military engineers faced severe mechanical problems operating tanks, trucks, and heavy machinery in desert environments filled with abrasive sand and extreme temperatures. Standard lubricants struggled under the conditions. Experimental friction reduction compounds were tested to prevent catastrophic wear during extended operations. Maintenance reports from that era documented promising results using molybdenum disulfide-based lubrication treatments. Engines exposed to severe heat and repeated dry start conditions often showed reduced internal wear compared to untreated systems. After the war, industries quietly adopted the material. Railroad mechanics used it. Mining equipment operators used it. Machine shops experimented with it. Farmers added it to tractors expected to survive decades of seasonal abuse. Long-haul diesel mechanics kept jars of the grey powder on workshop shelves beside grease guns and gasket scrapers. But somewhere over the following decades, public discussion around the compound slowly faded away. Not because the science disappeared. Not because the material stopped working. The automotive industry simply changed. Vehicles became increasingly complex. Financing cycles shortened ownership periods. Dealership servicing replaced independent repair culture in many places. Consumers gradually accepted the idea that replacing vehicles every few years was normal. Longevity stopped being the primary goal. Convenience became the priority instead. An engine lasting 500,000 miles with careful maintenance is wonderful for the owner. But from a business perspective, machines lasting indefinitely reduce demand for replacement parts, major repairs, and new vehicle sales. That does not require some grand conspiracy. Incentives alone naturally shift industries toward shorter ownership cycles. Meanwhile, older mechanics continued quietly using methods passed between generations rather than through advertising campaigns. One winter evening near Sugar Creek, another elderly mechanic demonstrated how he treated high-mileage engines. From beneath a shelf cluttered with carburetor parts and rusted hand tools, he pulled out a small glass jar filled with fine grey powder. "People ruin things by overdoing them," he explained. "This isn't magic. It's chemistry." His process was careful and deliberate. Fresh oil. Fresh filter. Engine slightly warmed. Then a very small measured amount of molybdenum disulfide blended into the oil before allowing the engine to idle quietly so the compound could circulate and attach itself to internal surfaces. Nothing flashy. No expensive machines. No dramatic promises. And yet the stories surrounding the results sounded remarkably similar no matter who told them. Cold starts became quieter. Valve train noise softened. Older engines idled smoother. Some vehicles consumed slightly less oil between changes. Certain towing engines appeared to operate at slightly lower temperatures under heavy load. Again, none of it sounded supernatural. That consistency is what made the stories compelling. Different mechanics in different regions described nearly identical observations despite having no connection to one another. And once attention shifts toward engine wear patterns, modern driving habits begin looking surprisingly destructive. Remote starts on freezing mornings. Short commutes. Constant stop-and-go traffic. Long idle periods. Engines repeatedly started and stopped without reaching stable operating temperature. Modern vehicles often experience more cold start cycles in a single year than older farm trucks once experienced in several years of highway and field use combined. A mechanic outside Millersburg once opened a relatively modern engine with barely 140,000 miles on it. The owner had followed dealership maintenance schedules faithfully. Premium synthetic oil, factory filters, regular service visits. Yet internally the engine looked heavily aged. Thick sludge coated the valve train. Timing guides were deeply worn. Oil passages showed contamination buildup. The engine had spent nearly its entire life on short winter commutes where the oil rarely stayed hot long enough to evaporate moisture and contaminants. The damage wasn't caused by neglect. It was caused by operating conditions repeated thousands of times. That realization changes how engines sound afterward. A brief startup tick no longer seems harmless. Cold idle chatter becomes more noticeable. Mechanical noise feels less abstract and more like evidence of friction slowly winning. Older mechanics often describe this awareness with another phrase modern culture rarely uses anymore: mechanical sympathy. Mechanical sympathy means understanding what a machine experiences internally and adjusting behavior accordingly. Warming engines gently. Avoiding aggressive acceleration while cold. Changing fluids early instead of late. Listening carefully to unusual sounds instead of ignoring them. Treating machinery as something worth preserving rather than replacing. That philosophy once existed everywhere in farming communities, rail yards, machine shops, and industrial garages because equipment represented survival and investment, not disposable convenience. A truck was expected to last decades. Tractors were repaired repeatedly instead of traded constantly. Engines were rebuilt because replacing them entirely cost too much for working families. Today, many vehicles contain layers of complexity unimaginable generations ago. Turbochargers, variable valve timing systems, direct injection, plastic cooling components, electronic modules, dozens of sensors monitoring every operating condition. Modern engineering achieved incredible gains in power, efficiency, emissions control, and comfort. But despite all the technological advancement, one reality never changed. Metal still rubs against metal. Friction still exists. Cold starts still create wear. Heat still breaks down lubricants. And every single morning, during the first seconds after the engine fires, tiny amounts of material disappear from inside the machine forever. Perhaps the deeper lesson hidden inside all these stories is not really about one grey powder at all. It is about forgotten patience, forgotten maintenance culture, forgotten respect for machines. Older mechanics often believed equipment reflected the attitude of the owner. Engines maintained carefully tended to survive longer. Machines treated harshly deteriorated faster. And maybe modern culture slowly lost part of that relationship. Vehicles became temporary. Repair skills became rare. People stopped opening engines and seeing the physical consequences of neglect firsthand. But somewhere in quiet workshops lit by old fluorescent bulbs and wood stoves, mechanics still remember what decades of rebuilding engines taught them. That longevity rarely comes from miracle technology. It usually comes from understanding friction, respecting limitations, maintaining machines carefully, and preventing tiny problems from accumulating into catastrophic failures over time. Because engines almost never die all at once. They disappear one microscopic layer at a time.